Thank you for the introduction. Like I said, I'm going to talk about these rim currents, what they actually are, and how to generate them. And I hope that during my talk I can convince you that we can generate long-range triplet Cooper pairs from these singlet Cooper pairs using the vortex magnetization of a single ferromagnet. So there's first a few people that I would like to thank for helping to shape this research. It was carried out during my PhD in the group of Jan Aerts, and I worked closely together with Kavi Lahabi, postdoc in Jan's time, and now continued with his own group at Leiden University, working on scanning squid on tip. And also detrimental, or not detrimental, but very important to the research was the hard work of these 4 master students that really did loads of samples and loads of structuring together with me. And the theory was done by Mikhail Salayev, who is based in Finland. All right, so I'll first introduce a bit what triplets are. It's not that needed after the excellent introduction by Wolfgang in the last talk. But so in a regular superconductor, electrons pair up with 1 spin up and 1 spin down electron. And that's why these Cooper pairs have a 0 spin quantum number. So we can write their wave function as this in this bracket notation. Well, triplet Cooper pairs have a spin quantum number of 1, and therefore they have 3 different spin projections, hence the name triplet Cooper pair. One of those spin projections is the M0 projection, so there's no spin projection along the quantization axis, and there's also 2 variants that actually do have along the quantization axis, and they either are aligned or anti-aligned with this local magnetization. And only those latter 2 can penetrate a ferromagnet over long length scales, so therefore we call them long-range triplets, or LRT, and the other ones we call short-range triplets, or SRT. All right, so how are they typically generated? Well, the classic way of generating long-range triplets is by the use of spin mixing and spin rotation. So it typically happens at non-collinear interfaces with superconductors to non-collinear ferromagnets, where the first ferromagnet makes sure that there's this phase difference between the 2 incoming electrons of the Cooper pair that generates this short-range triplet that cannot penetrate the ferromagnet over long length scales. But if there's an inhomogeneity of the ferromagnet at this interface, there's a rotation of the quantization axis, and therefore there's also the spin rotation process that can generate long-range triplets that penetrate the ferromagnet. This was done experimentally and also in the group of Norman Birch, that was already shown in the last talk. And this was already in 2010. And in the last 10 years, there's also an alternative way of generating these long-range triplets, and it is by the use of spin-orbit coupling, where typically these heavy metal elements like platinum are used to generate long-range triplets. Or for example, in this theory work, where there is 2 superconducting leads coupled to a ferromagnet, and there's a spin-orbit coupling interlayer there, and the relative orientation of the Rashba spin-orbit coupling and the magnetization of the ferromagnet determines whether there's a triplet proximity effect. But there's also one other alternative way of generating triplets, and that has so far only been studied theoretically, and that is by the use of magnetic textures, specifically magnetic vortices. So in these 2 works, there's a ferromagnetic vortex coupled by 2 superconducting leads, and it was found theoretically that they can induce a proximity effect, a long-range proximity effect. But the point is, this was not explored experimentally so far, and that is where we started our project on making very small ferromagnetic devices of roughly a micron in size. And our approach was these DISC devices that exist of 2 layers, a bottom layer made out of cobalt, which is the ferromagnet, which we structure into a disk, and then naturally a ferromagnetic vortex exists in the ferromagnetic layer. which is characterized by this whirlpool-like fashion of the spins going around concentric circles, basically. And in the middle of the device, there's a frustration of the spins, and locally the magnetization sticks out of plane. Then the top layer is niobium, is a superconductor. And what we do is we locally remove the superconductor along the diagonal of the device, thereby creating two superconducting contacts separated by the ferromagnet. So we make these devices using focused ion beams, which is these highly energetic gallium beams that allow us to structure not only the contours of the disk, but also the trench itself. So this way we can create Josephson junctions in a very narrow line cut of only 20 nanometers. Well, then the big question is, are they actually Josephson junctions? Do they actually have Josephson coupling? And in order to show this, I'm showing here the resistance versus temperature, where in dark blue, there's the curve corresponding to a disk device that doesn't have a trench, so there's no junction present. And what we see is that there's only a single superconducting transition, which is basically the superconductor shorting out the bottom ferromagnet. But once we structure the trench along the diagonal of the device, we see not only an initial transition owing to the contacts, but we see also a second transition corresponding to the weak link of the device. And to show you that this is really corresponding to Josephson behavior, we also obtained the AC response of our devices, and we typically see, while irradiating our samples with microwaves, that there exist these plateaus in the IV corrector, which are Shapiro steps, which is a sign of Josephson behavior. So we are entirely sure that this is a Josephson junction in a ferromagnet. All right. Then how do we know that the ferromagnetic vortex is responsible for generating the long-range triplets and not something else? In order to answer that question, we've made control samples shaped into a bar, and the natural magnetization of these bar devices at this scale is a magnetization along the direction of the bar. And we found that these devices have an initial transition corresponding again to the superconducting contacts, but at lower temperatures, we see that the resistance flattens out, and the residual resistance at low temperatures exactly corresponds to the resistance value where these two curves part, meaning we are measuring only the resistance of that weak link, which doesn't go superconducting. All right, so now that we established that we're dealing with these long-range triplets in the disk device, we would like to know how these supercurrents are distributed. To answer that, we can borrow a technique from optics, namely from the single-slit interference pattern that is typically found if you shine light on a narrow slit and then look at the projection of the light behind that slit. Then there exists this Fourier relation between the light projected behind the slit and the shape of the slit. There is a similar thing going on in a superconducting junction, as was found by Dines and Fulton in the early 1970s, namely that there's a Fourier relation between the superconducting interference pattern, so this is the critical current or maximum supercurrent the junction can sustain, and the magnetic field. And at the other side of the Fourier relation, there's the supercurrent density distribution over the junction. So this is already found by Dines and Fulton in the 1970s, but specifically for larger junctions, larger stack junctions. So we modified this method to also include planar junctions that are also laterally constricted. I don't have the time to go into the details, but if you're interested, you can check out this paper we did on that. And basically, takeaway message of this slide is that we're going to measure the critical current as function of field, applied out-of-plane magnetic field, and we're going to use this to extract the critical current density across the junction. So we have made a single junction, so what we expect is a uniform distribution of critical current, and that is typically this Fraunhofer interference pattern, which is characterized by a wide middle lobe and a sharp decay of oscillation amplitude as function of magnetic field. But when we actually do this experiment, we find something radically different. we find this typical squid-type interference pattern, or two-channel interference pattern. So here I'm showing you the interference pattern where on the x-axis with magnetic field, on the y-axis there's the applied DC current over the junction, and the z-axis is the color coding, which is the differential resistance. So basically this means that in the darker regions we have superconductivity, in the non-dark regions we have the normal metal regime, and the line between them is the critical current. So we see that this pattern is actually characterized by equal width lobes and hardly any decay of oscillation amplitude. And by the way, the bottom is a disk of 1 micrometer in diameter, whereas the top one is 1.6 micrometer in diameter. So we see that the oscillation amplitude also scales with the diameter of the device. So when we carry out this Fourier analysis, we find that there's two clear current channels, and these current channels are located at the rims of the device, so on the edges of the device. So if we scale the device to larger diameter, we also see that these two peaks in the Fourier analysis move out to the sides of the disk. So that's why we call them rim currents, because they run along the rims of the device. So I have some control experiments to show as well on the disks. First of all, a shallow trench disk. So here we don't remove all the superconductor from the trench of the device, which means that we're having an SSS type of Josephson junction, where the supercurrent is carried by a residual superconductor in the bottom of the trench. And we see this typical pattern, which is more reminiscent of a Fraunhofer pattern, which means a uniform distribution of critical current. And it is a bit distorted, which is probably due to stray fields coming from the ferromagnet that's below. But we also fabricated these junctions from a normal metal and a superconductor, and there you see there's a nice uniform distribution of supercurrent, namely this Fraunhofer pattern. So we know that if we're not dealing with a long-range triplet current, we also don't see these rim currents. All right, next piece of the puzzle comes from a follow-up project carried out by a colleague of mine, Yunxiang Yao, who continued his experiments using LSMO-based devices, and LSMO is an oxide material that is fully spin polarized. There were recently also experiments done on this by the group of Jacopo Santamaria, based in Madrid, and it was found that LSMO can be proximized over long length scales, just as in the classic result by Kaiser, the chromium dioxide result. But it's not entirely clear what the generating mechanism is here. So together with Yao, we made these devices that are either structured into a bar or in disks. And we see that in the case of a bar, there is still proximity effect. So the generator mechanism is different than in our cobalt disks. But we see that the critical current is distributed relatively uniform in the case of bars. Whereas if we structure this same device into a disk by subsequent milling steps, then we actually find that the critical current is distributed mostly on the edges of the device, namely these rim currents. So this leads to the conclusion that these rim currents occur only in disk geometries, and they only occur when long-range triplets are present. And I have to mention, we call them rim currents to not confuse them with edge currents, because edge currents are typically used for topological type of samples, and whereas here we're dealing only with simple cobalt and a superconductor. So therefore we call them rim currents. So we also had this vector magnet cryostat at our disposal in Leiden, and that allows us to not only probe the out-of-plane magnetic field, but also apply an in-plane magnetic field. And the nice thing is that if you apply an in-plane magnetic field, you can modify the spin texture and then use the out-of-plane field to actually study what happens to the superconducting transport. So first, as a reference, I'm showing you here a simulation of the magnetic texture at zero applied in-plane field, and then also the out-of-plane field interference pattern. And we see this typical pattern which is characterized by equal width lobes, namely this two-channel interference pattern. Now we will start applying an in-plane field as well as an out-of-plane field, so a constant in-plane field of 10 millitesla, and we start sweeping the out-of-plane magnetic field at the same time. When we apply this in-plane field, we start to deform the spin texture, and we start effectively to move away the vortex core away from the trench. So we start to displace basically the vortex towards the contacts of the device. And we again see this interference pattern that is characterized by equal width lobes, but we see a strong suppression of critical current at zero out-of-plane field, which indicates that we are dealing with a 0 pi squid behavior, or said in other words, one of our current channels has undergone this 0 to pi transition. Then if we start increasing this in-plane magnetic field to 40 millitesla, we find this peculiar pattern that is characterized by a very wide middle lobe, but actually an increase of oscillation amplitude at the neighboring lobes. And this is reminiscent a bit of a junction with many 0 pi segments in it. So there's these zigzag junctions, for example, where people study the superconducting transport, and they find that if you have many 0 pi segments, you can have interference patterns where the oscillation amplitude actually grows as function of magnetic field. So the takeaway message of this slide is that the superconducting transport is highly dependent on the specific spin texture of the device. Now, how do we actually generate triplets then, if the ferromagnetic vortex is responsible for generating the triplets? Well, first of all, we have to realize that it has to be a combination between spin texture and the edges of the device in order to produce these rim currents. And to answer this question, we teamed up with Mikhail Selayev, and he did an analysis on basis of the perturbation of the Usedel equations, which are these spin-charge-coupled diffusion equations for superconductors. And what he realized is that you can transform this vortex magnetization into a uniform one, but then within this formalism, a spin-orbit coupling term emerges. So, shown in a formula, once he basically does a coordinate transformation to transform the vortex magnetization into a uniform magnetization, you see that from the spatial derivative here, there emerges this spin-orbit coupling term. And it's well known that in cases of a spin-orbit coupling together with a Zeeman field, for example in these nanowire systems, that there exists a spin current that piles up at the edges of such a nanowire and creates a magnetization at the edges. A similar thing we think is also happening in our devices, namely that the spin texture acts as this effective spin-orbit coupling. This spin-orbit coupling together with the, well in this case not a Zeeman field, but the natural magnetization of the ferromagnet creates a spin current, and the spin current is carried by the short-range triplet condensate, which naturally occurs at the interface between the superconductor and the ferromagnet. This spin current adiabatically follows the local magnetization, but when it hits the edges of the device, this adiabatic approximation breaks down, and you actually see in the formalism that there exists this source of long-range triplets as well. So in a more picture-driven way, if we don't have any spin texture, so a uniform magnetization, we only have these short-range triplet Cooper pairs that naturally exist at the interface between the ferromagnet and the superconductor. So here shown as these two electrons that have these many different spin projections because they don't have a spin projection along the quantization axis. Now once we start curving the magnetization pattern, we start introducing a spin current carried by the short-range triplets that adiabatically follows the magnetization pattern. But when this spin current hits the interface between the superconductor and the vacuum, it is adiabatic approximation breaks down and long-range triplets are generated. So Mikhail also did a quantitative analysis of this, and he found that in if he places a vortex in one of our structures, so he assumes a ferromagnetic vortex in the simulation, he sees that there is these terms of these sources of long-range triplets at either side of the disk, which can explain the two-channel interference pattern. Now you could ask, why are these small indentations made into the sample here? Well, these indentations actually naturally occur as a byproduct of the FIP milling process, which you can also see here in the scanning electron image. But of course, if we wouldn't have these notches, we would still generate long-range triplets, since in the case if you don't have notches, but you have a slight misalignment of the ferromagnetic vortex with respect to the disk, which will always happen in a real-world sample, because well, the perfect disk is only a concept, then still you would have two source terms on either side of the disk. So there's still some open questions, namely, well, there's also a vacuum interface at the trench. So because the superconductor has a vacuum interface where you mill away the superconductor in the middle of the device. So why don't we generate triplets at this specific edge? And also, this doesn't explain yet why we have these many zero pi transitions or these many current channels appearing under in-plane fields when we start changing the spin texture. All right, so that brings me to the conclusion. We can generate these long-range triplets using the vortex magnetization of a single ferromagnet, and these are highly confined along rim currents running along the edges of the device, and we have a high control over the superconducting transport using this specific spin texture. Then in the last 4 minutes, I will show you one more thing, and that is, what about applications? Can we actually use this for something useful? Well, maybe yes, but let's say if we have this ferromagnetic vortex stable in a disk, and we start applying an out-of-plane magnetic field, we magnetize the disk, and you could say, well, these are two states. So you could use this, for example, as a memory element. But the problem is, once you remove the magnetic field, the disk reverts back to a vortex again. Well, in order to tackle this, we've also researched these elliptical devices, which actually have a bistability of the magnetic textures. So either there's two magnetic vortices at either ends, at either end of the device, or there is a uniform magnetization, which is a bar-like magnetization. So when we, and the idea is then we would make a Josephson junction on the side of the ellipse, and so either we have this ferromagnetic vortex stable nearby the junction, or we don't have any ferromagnetic vortex stable nearby the junction. So we should see a difference in critical current on basis of the magnetic state. And well, we made these type of junctions with the same FIP procedure as we did the disks. And indeed, what we see is if we go to the two vortex state, we find a higher critical current than we find in the magnetized state. So this could potentially be the basis of a new type of superconducting memory element, where you encode the information into a magnetic texture and read the magnetic texture out using a supercurrent. All right, so yeah, we found this way of making superconducting memory elements using these ellipses, and they have a robust electrical readout. They're stable at room temperature, and they require relatively low energetic switching with respect to conventional superconducting memory elements. And with that, I reached the end of my talk, so thank you very much for your attention.